Morning. Welcome to Krishna's class. Now we shall continue with the proof of the Riesz representation theorem. In fact, last time we proved that if a measure space exists which has been constructed out of the linear function with the properties that are listed in the theorem, then it is unique. So, uniqueness part we have done already. Now, we get down to the work of establishing that a measure space of the required type with the properties stated in the theorem does exist. Already it is unique. So let us do that. So we work with this existence of M and E. So what we want is, we want to show that there exists space constructed out of the given linear functional now, that is, we identify lambda, which is an element of CCX dual of that, it's a linear function of that. Associate this with this, a measure this is the work that we are going to do now. It's a longish proof that we have to give. You have to verify various steps. We start with the definition of the measure. Although we call it measure at the moment, we have not proved it, but we have to prove it that it's a measure. Or what I would say, a set function from, we start with a set function mu defined from R that means associating with every subset, a subset of X, a non-negative real valued function, which falls short of being a measure. Okay, so this is so, but mu is a measure on a script M. So we have to determine M. So M is a sigma algebra. and mu is a measure. In fact, mu is the measure that we are after. That is to be associated. So this is the job. So how to fix these things? Okay, so that's about the part. Now we define definition of the set function mu That's it. First we do it for open sets in X. Now before that, let me just tell you something, namely, see, X is a locally compact Hausdorff space, which means it's a topological space. Let V be an element of tau, that is, V is an open set V is an open set X. Now we first define mu on V, and then using that we try to reach out to all subsets of X. So let me do that. Let mu of V be defined as supremum of lambda f for all f subordinate. What does this mean? Now recall. So this is the definition that we are making. See, we have this. This is defined for all V that is open sets in X. Okay, so that is so this is the definition. This is the crucial definition that we begin with in fixing mu. Okay, now let me recall. This means f belongs to CCX, okay, and 0 less than or equal to fx less than or equal to 1, and support of f is contained. Okay, it is a compact support. We need not be a bounded set. There is no such assumption. V is open. V is any open set. What we are assuming is that f is subordinate to V, which means f is a continuous function with compact support on X, and the value of f is f lies between 0 and 1 for every x belonging to x, and support of f is contained in. So this is the meaning of this. We have done it earlier, so I am just recalling that. So now look at this. So lambda is now a map from CCX to R plus union 0. Therefore, this is a non-negative number, and for each f you get a non-negative number. So in short, you get a set of numbers, non-negative numbers. Now we take the supremum of that over all f subordinate to p as the mu of. Okay, so that somehow we are fixing the value of mu on v. Now, if we have fixed such a mu, then we first observe that it is a monotonic function. Now, mu is monotone in the sense that V1 contained in V2 implies mu V1 and that's obvious. See, you have V1 here and V2 here. Okay. Now you see that all these functions, that is f V2. So this is a larger collection. So we are taking the supremum over a larger collection when you compare with V1. So V1 is contained in V2. Okay. Therefore, from the definition, it is clear that supremum of lambda f for all f belonging to V2 is certainly less than the supremum of lambda f for f subordinate to V. Okay. Now, okay, let me just make some statement about this. Now, this is a non-negative real number. Mu v is a non-negative real number because you see that you are working on f, a continuous function with compact support. Okay. So lambda f is a finite number, non-negative. Now we are taking the supremum of all this. Okay. All such functions over V1 over, therefore this inequality is valid. So we have done it for open sets. Now from open sets, we go over to all subsets. Okay. Now definition of U. All elements of X. Px is the power set. Okay. So we are now extending it to all subsets of X. How do we do that? We do this as follows. Let E be a subset of X. E belonging to Px. Now define the form. Now you see, you can pack every subset inside an open set. Worst scenario, you will have to use X. So E you can put inside V. On several ways. So given V, see, this is your X, this is your E, not necessarily bounded or anything. You can put this inside a open set E. In the worst scenario, what you can use is, so there exists such an open set. Now for open sets, mu V is given. So we define mu of V as, for different V, you get a mu V. Okay. So you take the infimum of all that. That is the V that lies closest to E. This is what we are looking at. So you define this as infimum of mu V E contained in V such an infimum exists, because certainly they are all bounded. Mu is bounded below, for mu V is bounded below by 0. And therefore, it's such an infimum exists. Okay. So we have now made two representations. One, we first defined it for all open sets in X. Now using that, we have extended mu to all subsets of X. So whether our what we have defined here is consistent with what we defined for V. So the question that you ask is This is the question that you are asking. And that you can easily see it is so. Because if E is open, then E is contained in E, which is equal to this we take as V. And then the definition holds. And clearly mu of agrees with defined on. So there is no inconsistency in this extension. But now we have got extended to all subsets of S. Now what we prove is this. So the consistency part is taken care of. Now we want to prove that mu is countably subadditive That is the first thing that we try to. Okay. This is our first task. Now, one remark I want to make is this. Remark: in general, mu is not countably additive on X. So in general, mu is not countably additive on mu x, on Px. If it is countably additive, one could have chosen Px itself as the measurable spaces or the sigma algebra for our work. But if not, in general that is not true. Since that is not true, and countable additivity is a vital property or an important property of a measure, we have to throw out some sets from Px to get our what you call the sigma algebra or the measurable sets. Okay. So that is our work. So there is some subtlety involved here in fixing up where it is going to be countably additive. So we shall do that first. And although we are not proving it at this stage, later we will put all these things together and prove the vital results. Okay. So let me do that. So we see that in general on Px, mu is not countably additive. So we now search for where mu is countably additive. So we are just going to define a new collection. Okay, and call it this is the sigma algebra that we are building up. So what do you have? So let me just work out this. So before that we define this is the one that we first define. That MF we define by a set of all E contained in X, that E an element of Px, such that mu of E is finite and mu of E equal to supremum of mu of K, where K is contained in E, K is compact, okay. So let me make some remarks on this. Let me tell you what we are doing. What we are going to make as the definition of MF is an intermediary defining so what is it? It consists of all those E for which mu E is finite and mu E is equal to supremum of mu K, where K is contained in E and E is compact. So what we are doing is we are taking E. What we do is we try to approximate it from within. Earlier, you remember, we tried to approximate it from outside. That's how we defined mu E for every E. Now we are going to approximate it from within. This is your E by compact set. Say compact. So E is approximated from inside by compact sets. Now for compact sets you have mu K. Okay. So use that to get mu. What do we do? So mu E equal to supremum of mu K. Okay, so see, we have already set what mu E is for every E belonging to X, but only for a class of sets, not for every E, only for a class of sets, it can be approximated by compact sets from within, so that supremum of mu E becomes the supremum of mu K for all compact K contained. Okay, this is not in general true for everything. In fact, there are two conditions here. First of all, mu of E is finite, and for this is also true. So these two conditions are satisfied. So that defines. So this is an intermediate to identify. Okay, so we define M. So what is M? M is the set of all E contained in X, which E intersection K belongs to MF, where K okay. So what we do is we take E, okay. Now this is belonging to MF. Sorry, E is a subset of X. We take all those subsets of X such that this is a K which is compact in X. Okay. This part E intersection K is now contained in K. Okay, and it is contained in, right? So E intersection K has to be, we take this E intersection K is an element of this is the insistence that we make. Okay, so we take only those E need not be in MF. See, E need not be in MF. So here E need not be. But we require E intersection K to be in. Again, this may not be satisfied by all. Okay? So we get a collection of subsets which we designate by M as those with the property that E intersection K is in MF. Okay, for compact subsets. Okay, so that is the basic definition of M. Okay, so in general, properly contained. Now our claim is that X determined by That is one thing. And mu restricted is countably additive. It's a measure. Okay. So this is the basic work that we. So how did we work on this? I think one should be clear about what we did. Started with open sets. For all open sets, that means all elements of the topology we defined. And as a second step, we used this to define mu e. Okay, we use this to define mu e as the infimum of mu v where e is contained. There we approximated e from outside. Then what next? The next step was we worked on or we made a special collection of subsets, picked a special collection of subsets from Ex with this criteria that mu of E is finite and mu of E is obtained through approximations of E from within using compact sets. Okay, by taking the supremum of mu k for all k compact and such that k is contained. That is the definition. So such collection we called MF, and M is identified as all those E belonging to or contained in X with the property that E intersection K belongs to MF for K compact in X. Now we claim that such an M is a sigma algebra on X determined by lambda, and mu restricted to M is the measure. This is what we have to prove. It's a long way to prove this. Okay. So we start working out these details. Measure space determined by the given lambda. So this is what we are going to. It is in the dual of CCS. That's what we are doing. That is M and mu have the required properties. Now we start proving bits and pieces of that. Okay. First thing that we prove is mu is small. So you have mu A. Suppose A is contained in B. This is true for every A and B. Okay. This is true for A and B belonging to Yes, this is true. Now that is obvious. That is obvious because you have A, you have B, now look at the definition of mu on A and B. You will see that clearly mu A is because see A, see you take all open sets B that contain B, they contain A also, but all open sets containing A may not contain B. So it's a subcollection. Therefore, when we take the definition of mu as the supremum of mu E as mu A and mu B you take as the infimum of mu B, E contained or A contained in B and B contained in B, compare them, it's clearly mu A is less than or equal to this we have seen. We already seen this. Now, another thing that we want to do, another thing that we want to prove is that mu E equal to 0 implies E is a subset of. So what are the requirements for an E to be in MF? Okay. E to be in MF, you need mu of E to be finite. So the first condition is obviously satisfied. Okay. The second condition is that mu E should be supremum of mu K compact in E and K compact. Now you see that E take K contained in, so mu K is going to be less than or equal to QE, which is equal to 0, which implies mu of K equal to 0, compact K contained in. What does this mean? This means when you take the supremum of mu K, you immediately see that supremum of mu of E compact contained in B. Now you see that this is going to be 0. Take the supremum of all that, then you get mu E equal to this satisfies. So you see that mu of E equal to this, because this is 0, so this is 0, and this is 0, so this is satisfied. Therefore, E is E belonging to. So if mu E equal to 0, means E is an element of F. That is clear. So what more you get from this? Further, we see that E belonging to M implies and then A belongs to and obviously A contained in E, mu A, if this is equal to 0, then you have mu A equal to 0. Okay. So if A, E intersection K is E intersection these two properties are satisfied, which implies A belongs to MF, and using that you can show that equal to 0. What does it mean? This means that mu A equal to 0 for every subset of E. If E happens to be an element of M, then every subset of A also, every subset of E also belongs to M. And using this, you get this result. That's quite easy to see. Therefore, what does it mean? It means that U is complete. This is the requirement for mu to be a complete measure, but we have not said it is a measure yet. But the completeness property that is required of mu is now satisfied. Okay. Further, for every E belonging to M, that is clear. That is clear. So this is of course the definition that you have for mu on for any subset, and therefore in particular for all subsets of. Okay. Now what next? So now our task is to show that mu is countably additive. I mean countably subadditive. So that mu becomes countably subadditive on M also. This is now we are going to prove it on Px. Okay. Therefore, once we prove that, we get countable subadditivity on script M. So let us do that. Now this is the major part of the work today. So we have identified script M. Now our task is to prove that script M represents a sigma algebra. So we are slowly proceeding towards that. Okay. So first we observe that lambda positive implies what do we mean by that? That is, if f is less than or equal to g, so how do we, we get it immediately. Lambda g, let us write this as, this you can write as lambda f plus lambda of g minus f. Because lambda is linear, you see that this is okay. So what does this mean? So you see that it is lambda f plus, what do you get? G minus f is G minus f is positive. Okay, and lambda g minus f is positive. Therefore, what do you get? You get from this lambda G is bigger than lambda. So we observe that lambda F is less than or equal to lambda G. So that we have some monotonicity has been established. Now we are in a position to take up the countable subadditive property. Okay. So first step is mu is countably what is that? That is mu of if E1, E2, etc. are arbitrary subsets of X, then mu of union I equal to 1 to infinity I is less than or equal to sigma I equal to 1 to infinity mu. Now these are all non-negative terms. That's what we have seen here. Okay. Right? And we have this, what we assert is that this is going to be true. This is subadditive. Now on script M, we can later prove that additivity, countable additivity is valid. So we just make a remark. On countable additive. This we shall prove later, because we need this to assert that script M is or mu is a measure. Okay? And when this so later when we want to that is a measure, we need this consideration. Okay, so let us go. First observe that mu of this is the first thing that we prove. Okay, so to prove this, to see this, choose G subordinate to. Now if V1 and V2 are open sets in X, then V1 union V2 is an open set. Now you choose G such that this is true. That means the following: G belongs to CC into, or rather, synapse. Then support of G contained in V1. These are the requirements. I mean, this is the meaning of what we write here. Okay. Then of course what we have is there exists H1 and H2 such that HI is subordinate to VI for each I, and this is actually a partition of unit. So you have V1, V2. So we get H1 and H2 such that HI is subordinate to VI and H1 plus H2 is equal to 1 for every X belonging to Now there are two things. Look at the support of G. Support of G is a compact subset of V1 union. Okay. Let us try to understand that step. Support of G is compact. It's a compact subset of V1 union. And what we do is, so you have got V1 union V2. This is V1 union V2. Suppose this is the support of G. Okay. And this is support of G. So what we do is, we look at support of G, see look at this part. So support of G, one part, support of G intersection V1 and support of G intersection V2. So there are two sets like this. Okay. Now what we can get is, we can get a result of this kind, namely that support of G V1 Similarly, support of V2 and H1 plus H2 equal to 1 on this is possible. Now this is a sort of breakup of the the of the or partition of unity that you work out. Okay. Therefore, now clearly Hij is subordinate to, that is support of Vidya. This is what. Okay. And further, G is equal to H2G on support. Therefore, what do you get? Get lambda of G equal to lambda of the linearity lambda. And this is of course less than or equal to mu of V1 plus mu of V2. That's a definition. Okay. Now this inequalities, from this inequality, it follows that for every E2, this for every G subordinate to V1 union U2. Therefore, now what do? You have to work on E1 union E2. Okay. So we cover E1 union E2 by a V1 union. Therefore, of course, straight away therefore we have this. Our first assertion is this: mu of V1 plus mu of, that's the first part. That is true for all open sets V1 and we shall use this. So now what we assert is the following. So we claim mu of this is what we want to assert. This is the subadditivity property. Okay. First step is case 1. First case that we consider is mu ei equal to infinity for some I. Then what happens? This becomes infinite. Okay? And you see that in any case what happens is whether it is infinite or finite, this is going to be so. Then you have mu of so it is trivially satisfied. So now we take the case. So case 2. Assume finite for every I. Then we want to assert this, the inequality. Now we choose an epsilon positive. Arbitrarily chosen epsilon. There exists open sets Vi containing Ei such that mu Vi is less than mu Ei plus 2 to the power minus I. So 2 to the power minus I, epsilon is a positive. Therefore, what you have is this. You have Ei. Ei can be approximated as closely as you want to Ei, so that you take mu Ei, then this is this. If you add 2 to the power minus I epsilon to mu Ei, it would be bigger than mu Ei. And that follows from the definition of, this is a consequence of so what we have mu E, see we have this mu of E is equal to what you call infimum of mu V, V open this is the definition. Namely, that's a simple consequence of that, and this is true for I equal to therefore what we have is and this is open. Okay, now you see that choose subordinate to. Now, since F has compact support, see, you have this is support of which is contained in V. V is the union of this countable union of Yes. Therefore, what you get? V turns out to be the collection Vi is an open cover for support of F. Since support of F is compact, there exists a finite subcover. What does this mean? This means the following. There are finitely many VIs which encloses this support of F. That is, F is subordinate to N for some Vn belonging to Vn. Therefore, there are finitely many. You can just find out this, and you see that support of F is contained in this because support of F is a compact subset which is contained in the union of VIs. Therefore, you get a finite subcover. Therefore, now what we have is this lambda F. If you work out, this is less than or equal to mu of V1 union V, which is less than or equal to mu of N. That is because of the monotonicity and what is called the subadditivity on this set, and this you have is less than or equal to sigma. Now we use this inequality. If you use this inequality, this is less than or equal to I equal to 1 mu Vi plus epsilon. Because when you sum this up, you get epsilon. So this is the inequality that you get. Now, since this result is true for every F having its support in the union of VIs, infinity, it follows that contained in V. It follows that mu of EI is less than or equal to mu of V is less than or equal to epsilon. Since epsilon is arbitrary, you obtain mu of less than or equal to now this is the property that we want. This the subadditivity property of countable subadditivity property of mu on so that is what we wanted to do today. Okay? So we have completed the proof. Now what we want to do is, now you see, for every EI this is countably subadditive. Now what we do is we pick from this the collection belonging to M, and for those and for that collection script M, we prove that this inequality can be strengthened to additivity. That we shall do today, because this is a crucial step in proving that mu is a measure. Okay, so if you go through the definition of a measure, it's a additive, it's a countably additive set function defined on okay, it's a countably additive set function defined on the sigma algebra M. Okay, in the sense that when EI is a collection of elements in M with EI's what you call pairwise disjoint, then this inequality can be strengthened to inequality. That's the result. Okay, so that condition is there, additional condition is there. But see, in general, on script M, or sorry, on Px, even if you take pairwise disjoint EI, this may not be. That is the problem. That's why we throw out, throw out several subsets from Px and get the collection script M, and we prove that this is the structure of a sigma algebra, and then mu becomes a countably additive function in the sense that union of mu of union of EI in that case become equal to this, provided EIs are pairwise disjoint. Okay, so thank you very much. I stop here. It's a long way to go. There are a lot of things to be proved, remain to be proved. As you know, we have only defined something. We have not proved anything regarding the structure of M.